All right, today is January 10th, 2012. Chapter 7 review. We already did several questions yesterday, and we did 4A and B. So we're going to start on 4C. It'll be like a review of A and B. They've given us a number in radical form. So it says the fifth root of 1024. So what they're looking for is some number to the fifth will be equal to 10,024. Or in other words, you multiply that number 5 times by itself, it will give you 1,024. Okay? That's the general idea behind a radical. Now the question is actually asking you to put it into exponential form. So this is the formula for changing radicals to exponents and exponents back to radicals. Okay? So right now we're in radical form. We have our base. So our base is 1024. That's still going to be the base of our question. Okay? So our base will still be 1024. A is the numerator. The numerator in this case, what number would it be? 1. That's right. If there's no number there, it's assumed the number is 1. So our numerator is the number 1 for the fraction. That's the exponent. The denominator is the number on the bottom. Or in radical form, it's the number on the root. So this would be 1 over 5. So in other words, this is written as 1024 to the power of a fifth. Okay? So that is radical form changed to exponential form. Now we can actually solve this too. If this is asking just for a positive exponent, that's the answer we want. This is a positive exponent. If they ask us to evaluate, okay, I don't expect you guys to know this off the top of your head, so we'd be evaluating. This is the symbol it looks like on your calculator. I'm going to draw it. Chris? Is it 4? Okay, we'll check it out on the calculator, make sure. You'll have a symbol that looks like this, okay? This is your root. It's telling you your x value. You're going to plug it in. So it's not square root. On your calculator, square root has a 2, and cubed root has a 3. In this case, we have a fifth, so I don't have a specific button for that, so I have to use this. I'm going to type in my base. Everyone's calculator is different. You might have to do this in a different order. 1024 to the fifth root. I put the number 5 in, is equal to 4. So yeah, you're right. If we evaluate this, the fifth root of 1024, when evaluated, is equal to the number 4. So 4, when we multiply it times itself 5 times, will give us 1024. So your button could also look like this. It might be a base of x and an exponent that's a fraction. You have to find, each of your calculators are probably different. And it makes sense because we're changing from an exponent with a fraction to radical form. So you're either going to have a button that's in radical form or it's in exponential form with a fraction as the exponent. Question 4D. In this case, we are in exponential form, okay? They want us to change it to radical form, but I'm not dealing with a fraction right now. I'm dealing with a decimal. I need to change this decimal into a fraction, okay? I'm hoping you guys remember how to do this. Yeah, it will be 1 over 5. The way you do this, okay, we'll do it as a side calculation. 0.2 divided by 1, okay? This is what it's going to look like as a fraction. Technically, this is 1.0, okay? So 0.2 divided by 1. What you guys are going to do is you're going to multiply this so that the number on top is a whole number. So I multiplied the top and the bottom by at least 10. I might go by 100. Let's see. When I multiply 0.2 by 10, I'll get 5. Oh, yeah. And when I multiply, that doesn't make sense. Yeah, why did it say 5? That didn't make sense. Yeah, it's definitely 2. Okay. There you go. 2. And 1 times 10 is 10. So we have 2 over 10. We need to reduce this, which is equal to 1 over 5. Okay? So we know that our fraction is going to be 1 over 5. So I change my fraction form to the base 16,807 to the power of 1/5. And now, according to our radical exponents, we change this, okay? So in radical form, we have a root. We know 16,807 will be our base. What power do I put 16,807 to? That's right, put it to 1, which means it really doesn't change it. And what root will this be? The 5th root. Good. So that's it in radical form. We did the same process we had done above.
Answer is 7.
Okay? Yes, and if we were to evaluate this, 16,807 to the 5th root is equal to 7. I don't know why it gave me a decimal. It's 7. So just to recap, what we did here is I needed this to be in fraction form. We knew we could make any number a fraction by putting it above 1. So I put it over here, 0.2 above 1. I multiplied the top and the bottom of the fraction by 10. I got 2 over 10, so now I'm working with just whole numbers. Oh, I forgot about that. Okay? And then I reduced the fraction to 1 over 5. So that's it in lowest form. We want our exponents to be in lowest form. Okay? If you have a fraction, make sure it's in lowest form. It's usually only one step. We're not going to be working with very complex fractions for this. Okay, 4e. Now we're in what form right now?
Oh, that's what's it called? Radiant.
Yes, radical. Good. We're in radical form right now. So we need to change this to our exponential form. So in order to change this to exponential form, we're going to use that little formula once again. Our radical exponents. We'll underline what we have. This is our base. Negative 216 is our x. Our a is 3. And our b is 3. So when I go to put it in exponential form, we still have the same base, negative 216. Our base is the same. What number goes on top of the exponent? Yep, 4 over 3, which is our a and our b. Okay? So that's in exponential form, negative 216 to 4 over 3. Now the difficult part of this would be to evaluate it. Okay? To evaluate, imagine we're dealing with brackets. The underneath of the root is what we deal with first. Okay? So negative 216 to the power of 4, I'd put that in my calculator. To the power of 4. Very large number. I then find the third root of it. To the third root. Yeah, 1,296. So if we were to evaluate, we get 1,296 as our answer. This is question number 2 for page 423. Question A. They want us to graph an exponential function. So we have a function y is equal to 3 to the power of x. Okay? 3 to the power of x. They want us to graph this. They're telling us 4 things we need to determine. We need the y-intercept. That disappeared. We need to sketch it. So sketch is not spelled that way. S-K-E-T-C-H. They want us to get domain and range. And a horizontal asymptote.
What?
You will not be asked this on your test. Well, I'll tell you what it is anyways in case you need to do functions in grade 11, university, or 12. You may be asked to graph it, but I won't ask you about a horizontal asymptote. Okay?
Okay, I'll do it.
So what this is stating here right now, and these numbers aren't going to really help us too much, we've been better if we had a blank one. We need to graph this function, okay? When x is any number, we need to find out what y is. So we can make a chart for this, okay? What we can do, we make a t-graph. Now, these are x functions and our y functions. Remember, it says y is equal to 3 to the power of x. So we plug numbers in. Now, our graph we have here goes from negative 10 to positive 10. So normally you would start at negative 10 and you need to plot all of the points. So when x is negative 10, so our very first example would be y is equal to 3 to the power of negative 10. This is going to give you a decimal number. Okay? The reason for that is because, remember, if I were to make this a positive exponent, it becomes y is equal to 1 over 3 to the power of 10. So you have 1 over a very large number. When 1 divided by a very large number, it's pretty much almost 0. It'll be very close to 0. So let's put it in. 3 to the power of, yeah. So it's closer to 0 than it is 1. So in other words, you have a number, it's not quite at 0, but it's very close to it. We're going to jump ahead a few, just so you get the idea. Let's go to negative 4. Y, 3 to the power of negative 4. Again, that's 1 over 3 to the power of 4, which is 3 to the power of negative 4. Again, a number closer to 0 than 1. So we have very, very small numbers right now. We're going to jump over again to, let's go to negative 1. Okay, I want you to think about this. Negative 1. Well, when y is equal to 3 to the power of negative 1, that's equal to what? Yeah, 1 over 3. A third, 0.33. Okay? So when we go to graph that, our y value is 0.33, so it's somewhere here. Now, this is where we start to get important ones. With growth, the left side of your graph is not going to be touching 0, but it's going to be very close to 0. Our y-intercept is going to be important. That's when x is 0, right? Whenever x is 0, that's a y-intercept. So we're going to solve the very first one. When y to the 3 to the power of 0, what does that equal? 1. 3 to the power of 0 is 1. Okay? Unless your number is multiplied by something, all exponential equations, y-intercept will be 1. Whenever you put a number to the power of 0, you guys get what? 1. So we know our y-intercept will be at 1. So we've been very close to the x-intercept, and all of a sudden, we start moving up. Okay? I know that's not perfect, that line. Then, let's start thinking of our numbers. What about when we're at 1? I want you guys to see how fast this growth is. What is 3 to the power of 1? Just 3, right? So we got that. So already when x is 1, we're at 3. What about, yes, when x is 2? 3 to the power of 2 is 9. So already, we're at 2, we're already at 9. Yeah, the next one's 27, and it just kind of takes off, okay? So this would be an example of exponential growth. We're going from a very small number to a large number, so exponential growth. Not negative numbers. So let's just talk about a few other things. We've done the y-intercept. We know it was at 1. We sketched this. Domain and range. What's the domain of this function? XER. This number stretches all the way to negative infinity to positive infinity. It goes forever. So our domain, XER. Now our range is a little tricky. What is our range? Yep. There's something. Does it go below the x-axis, guys? No, it never will. It never, ever will. Y is greater than 0. That is our only restriction. Y has to be a positive number. So y is greater than 0. It is not greater than and equal to, because remember, like I told you, you'll never touch 0. So we're going to do this again. This time we're going to use our second number. Y is equal to 0.25 power of x. Now remember, we're going to put it on the same graph. Our graph went from negative 10 to 10. So again, I'm going to start at negative 10. I want to show you what this number is going to look like. So we put y is equal to 0.25 to the power of negative 10. Okay? If I was to make that a positive fraction, it becomes 0.25. 1 over 0.25 to the power of 10. Okay. When you multiply 0.25 by 0.25, does the number get smaller or bigger? Smaller. 0.25 times 0.25. Oh yeah, much smaller. So if I continuously do that, I'm going to get 1 divided by a very small number. Okay, so when we have 0.25 to the power of negative 10, huge number, 1,000,000 and something. Okay, so clearly that's going to be way off our chart. So we're again going to just try to work with numbers close to the y-axis. So we're going to skip a whole bunch. Let's think about this. Let's go to negative 1. Okay? Y is equal to 0.25 to the negative 1 gives us 1 over 0.25. Anyone know what that equals? 4, that's right. Our number is 4. So let's get a general idea here. When we're at negative 1, our y value is 4. So we have some graph, okay, that comes from up here and comes, try to make it straight, comes flying down, okay? What about when when x is 0? That's right? Any number to the power of 0 is going to be 1. So 0.25 to 0 is 1. So our y-intercept, again, is at the exact same point. See how we ended up at the same point? So we're coming down. Now, what do you guys think is going to happen? It's going to level out. Will it touch the x-axis? Won't touch it, but it's going to come very close. It's going to look almost the opposite of our other graph that we had. This is a decay model. So let's think of this now. At 1, whoops, that's not 4. That's right, it's 0.25. Y is equal to 0.25 to the power of 1. Well, it's just 0.25, or a quarter of the way of 1. So we go back up and plot that point. It's somewhere down here. And then we just imagine everything gets closer and closer to the line without ever touching. Okay, so that is exponential decay. That's exponential decay, our blue model. We drew a y-intercept, we sketched it. What's the domain of this? Yep. It's going to go on forever. Exactly, same range. Y-E-R, such that, yeah, for these, okay? Now, it changes a little if more numbers are added to the equation, but, okay, so we have this formula. It's talking about population growth. This is also has to do with interest growth. We'll get into the next chapter. But we're talking about population growth today. This P stands for your final population, okay? This is what we're essentially looking for. So P is equal to, this is P naught, okay? All that means is our starting population. Whatever our population started with, that's where you put the number. It's multiplied by 1 plus I is your growth rate. So if your population is growing by 3%, that would be 0.03. If it was decaying by 3%, you'd be minus 0.03. Okay? And n is the number of periods. So if it tells you it's growing 5% every year for 9 years, then n would be equal to 9. So over the course of 9 years. So we're actually do a question here. A city has a population that increases 3% every year. In 1990, the population was 110,000, okay? So what they're telling us is I is 3%. Now remember, to put I into the equation, I have to make it a decimal. What would 3% be as a decimal? Yeah, 0.03, okay? It also says that in 1990, so that's going to be our starting year, the year 1990, your population was equal to 110,000. That's probably going to be our P naught, okay, our starting population. So our P naught in this case, P0, is equal to 10,000. Sorry, 110,000. Our I was 3%. And the question is going to ask us, what is our population in the year 2006? Okay, so year 2006. So let's go to our formula. We have to solve for P, that's our population. P naught, we know what it is. I'm just going to rewrite the formula out. So we're solving for P. Starting population is 110,000. 1 plus the growth rate, 0.03. Now here's the question. This is the tough part. N, number of periods. How many periods does this compound over? How many? 16, that's right. Compounds over 16. From the year 1990 to the year 2006. There are 16 years here. So our N is going to be equal to 16. So we plug 16 in. Now, once we have all our variables, it's very simple. We just plug it into a calculator. So 110,000. The question says 2007. All right, well, we're going to go with 2006, okay? Ours will be a little different. To the power of 60. So 1.03 to the power of 16. Okay? Do not round that number. You need to multiply that number by our starting population. Multiply by 110,000. So it gives us 176,517. Now this is a population, so 0.7. We don't really have a 0.7 of a person, so we're going to just round it down. No, we're not going to round it up. We're just going to round it down. Okay? Well, that means somebody's in someone's stomach or something. They're about to give birth. We're not going to count them yet. Okay? They're not out yet as our population. So as a census, we wouldn't count about to give pregnancies. Okay, so in the year 2006, there will be 176,517 people in this town. Okay, this would be part B. The question asks us, how long does it take for the population to reach 150,000? So we have to make sense of this question here. We still have our formula, P is equal to P naught. This is a growth rate formula. Exponential decay or exponential growth. So let's define ours. Now remember our starting population was 110,000. We know our interest rate was 3%, and as a decimal it's 0.03. And they're asking us for the population to reach 150,000. So that's when P is equal to 150,000. So we're actually going to be solving for the exponent here. This is something we haven't done before. So we'll plug these numbers in. We get 150,000 is equal to 110,000. 1 plus 0.03 to the power of n. Okay, I'm going to solve the brackets. We get 1.03 to the power of n. Now, I need to isolate as best I can. I'm going to move 110,000 to the other side, which means I have to divide both sides by 110,000. When we do that, these two cancel out, and we're going to get 1.03 to the power of n is equal to 150 divided by. So we're going to round this number to 1.364, we'll say. Okay, now this is where we run into a bit of an issue. This is where we have to work with trial and error, okay? We have to figure out what exponent, that's going to be the compounding period, is going to change 1.03 into 1.64. Now we know it won't be 1. Is there any high number we know it won't be either? 2 is another. What did 16 give us after 16 years? It gave us a population of 176,000. That's too high. So we know it's going to be a number between 1 and 16. So we're going to use a little bit of trial and error. Again, we'll use a T-chart. Okay? This will be our N and our Y. Now we know when N is 1, 1.03 to the power of, give us our equation, gives us 1.03. That's not going to be enough. So we're going to jump up a few more. Let's go up to 10. See what that gives us. Y equals 1.03 to the power of 10. Oh, wow. Oh, no, that's not exactly it. Good. I almost got confused there. Thought we guessed right on the first try. 1.343. That's not quite what we're looking for. So we have to go a little higher. Let's try maybe 13. Is it? 13, 1.03 to the power of 13. Oh, yeah, you're right. That number is too high. 11 gives you 1.38? Perfect. Okay, that's what I wanted to find. 1.6. So in between, we discovered that 1.03 to the power of 11 gave us a number that was too high all of a sudden. So this is how I want you to answer this question. We know that somewhere in between 10 and 11 years from 1990, the population reaches 150,000. So from 1990, that's where we started. Between 10 and 11 years, 10 years from then will be 2000. And 11 years will be 2001. So your sentence will be somewhere between or in between the years 2000 and 2001. I want you to give me a range, okay, of a year. Between the years 2000 and 2001, the population equals 150,000 people. Okay, so we're not going to get it dead on. I don't expect you to get it dead on. I want you to give me a range within a year. Between what 2 years will the population reach 150,000?